Hello everyone, Human Hard Drive here. Today on Electronics 101, we're going to be talking about AC, alternating current, and some of the things you should know if you're going to do anything in alternating current. So, let's jump right in. A little heads up though before we start. This video is going to touch on a little bit of complicated math. I'm going to try and work my way around it as best I can while giving you the information you need, but just be aware that I might say some things that might not make immediate sense to you because they do involve a little more complex mathematics. But again, I will try and keep things nice and neat. So with that, let's go ahead and get started. So what is AC? AC is a time-dependent system in which the current alternates. So you've got time and you've got current, voltage, that should be an I, not a C. Voltage, current, doesn't matter. And it's going to vary in some way. So it could be a sine wave, it could be whatever the heck I just drew. It could be a triangle wave, sawtooth, square, whatever. It just has to vary in some way with time in a somewhat regular manner. Otherwise it's just noise. But yeah, that's what AC is. It's a time-dependent system that varies. So, sine waves are going to be pretty much a theme here because a lot of the mathematics is derived from sine waves and the relationship of sinusoidal waves, sine waves, or cosine waves. So, let's talk about some things. A lot of things stay the same as with DC. You still have voltage, you still have current, and you still have power, and you even have resistance, there we go, that's how you spell it. But some things are going to be added. So you have peak voltage, you've got instantaneous voltage, you've got RMS voltage, again peak, instant, and RMS, which is really the same thing, but and the same goes for power. You've also got real power and total power. Resistance, a couple things are different. You have impedance, and you have capacitance, reactance. All things we're going to talk about in this video. We're going to try and fit it into a decent time length. Okay, so let's start with voltage. I'm going to draw a sine wave, or at least attempt to. And that looks pretty good. Okay, so peak voltage is that right here. Generally, an AC wave is going to go from peak to negative peak. You have the instantaneous voltage, that's time, which is any point along this curve. And then you have RMS, which is right here. RMS is V peak sine pi over 4, or for those of you who like degrees, V peak sine 45. And for those of you who don't know trigonometry, it's about 0.707 V peak. That is the RMS voltage, the root mean squared voltage. What is the RMS voltage? RMS voltage, or also known as the effective voltage. RMS voltage is, say you have a resistive element like a stove, and you pass 120 volts effective voltage AC through it. If you were to pass 120 volts DC through it, you'd see the same current as you did in the AC system. That's what the RMS, or effective voltage, is. Effective voltage is also what most multimeters that will read an AC voltage measure. They will tell you the effective voltage. So your outlet here in America is going to give you 120 volts effective voltage. So its peak voltage is actually just slightly higher, but its effective voltage, the thing everything operates at, is that effective voltage of 120. Because that's where everything stays the same. Okay. Same goes for current. You have peak, RMS, instantaneous, all the rules apply. However, Ohm's law is a little different, which is where we get into resistance and its variations. But before I talk about that, I'm going to talk about adding some things. Sine waves are important in this. Being able to do trig is pretty important in this. Vector addition is also very important in this. So let's say I have two sine waves. Just looking for... That's pretty good. So let's say we've got two sine waves, both of equal voltage, equal peak voltage. Let's say 5 volts, 5, negative 5, 3, 5 volts, negative 5 volts. Now, remember this is a time-dependent system. Another thing you have to remember is phase shift, and this is going to come back later. Phase shift is important. So let's say these two waves are 90 degrees out of phase. What does that mean? So I've got, let's draw another coordinate system. There we go. So I've got one sine wave here. That's pretty good. And then I've got another sine wave here. That's as close to 9, and I'm shifting to 180. Can I just undo that? Ooh, too far. Try that again. Starts here. No, that's why I'm doing it wrong. Starts here. There we go. And down. That's 90 degrees. That's better. Okay. So, we're going to add these two voltages together. How do you do that? Well, these are 90 degrees, so we create two vectors. We'll call this A, we'll call the red one B. So you have, there we go. So here's voltage A, here's voltage B, and the difference between these two is 90 degrees. What is the resultant vector? Well, in this case, it is... You can do it one of two ways. You can realize that, A, this is 90 degrees, so you know that the voltage sum is the square root of VA squared plus VB squared. Or you can do the head-to-tail vector addition, which you have to do if the angle between them is not 90 degrees, and you still get... Well, you get whatever this is here. Because they're the same VA or VB root 2, I believe, is the VA root 2. So that's how you sum the voltages in an AC system. You have to remember that it's time dependent, so phase is an issue that you have to remember. So that's how you do addition. And I'm kind of glad I brought up phase shift now, because that's going to come in later. So let's talk about current and how that's calculated. So if you remember in DC, there's something called Ohm's law. Ohm's law for DC says V equals IR. AC, V equals IZ. What's Z? This is impedance. Now this is where the trickier math comes in. Impedance is the complex relationship, meaning part of it is real, part of it is imaginary. In electrical engineering, the imaginary constant you normally see as I is denoted as J. I don't know why. It probably has something to do with the fact that there's already an I, but who knows. So it's the complex relationship, so some of it's imaginary, some of it's real, between, come on, there we go, resistance of an element and reactance of that element. And the resultant vector between those two is, of course, impedance. Okay. And yeah, there's some angle here, theta. That angle between the two is going to come in later. But that is what impedance is. So, in AC there is an element of resistance. A resistor has an impedance R. It has no reactance. You can think of this as two things. Resistance is just magnitude. All it does is reduce the current through the system. Impedance is a combination of just that resistance and also a time-dependent component, that phase shift. What reactance does is it doesn't change the current, it doesn't change the amount of current, it changes the phase of current with voltage. Again, AC is a time-dependent system, so phase is a factor. Okay, now, in the world where there are three passive components, the resistor, the capacitor, and the inductor, two of the three are time-dependent components. Resistor is not one of them, so that just kind of leaves the capacitor and the inductor. The impedance for a resistor is just R, and in an ideal world, the impedance for a capacitor is just the reactance, and the same is true of the inductor. However, there is some level of resistance in both these components, but we'll talk about how to calculate that in just a moment. So let's talk about reactance. Remember, reactance causes a phase shift. It causes the current to be out of phase with voltage. For the capacitor, reactance is given by 1 over 2 pi Fc. And for the inductor we're going to talk about in a later video, reactance is given by 2 pi FL. For those of you wondering why there's a 2 pi here, technically this is denoted 1 over omega C, and this is denoted omega L. Again, this is the conversion from radians to degrees. If you want it in degrees, you use this. If you want it in radians, you use this. So what can we see from this behavior? Well, we can see that, I should probably mention units. They're all given in ohms, and ohms. Yeah, I'll mention that now. Okay, so what can we see from the behavior as given by these formulas? Well, we can see that as frequency increases, the reactance of the capacitor decreases. So you get a smaller and smaller reactance, whereas with the inductor, you see that as frequency increases, its reactance increases. So you're going to see a bigger and bigger phase shift. You're going to see a bigger and bigger change. You're going to see a bigger deviation between the current function and the voltage function. Okay, now let's say in this ideal world, in this non-ideal world, there is some resistance. That's easy enough to calculate. Remember, it's a complex relationship, and these are at right angles to each other. So what we can see is that the impedance for this is just going to be RC squared plus XC squared, and for this it's just going to be RL squared plus XL squared. That's an L, not a C. Where's the eraser? There it is. Okay, so that's what reactance is, and that's how Ohm's law translates to AC. Now comes the complicated math bit. This is an extreme oversimplification of Ohm's law for AC. Ohm's law for AC actually looks like this. I'm going to ignore the magnitude for just a moment. V, E raised to the J, omega T plus phi V equals I, E to the J times the magnitude of omega T plus phi I, times Z, E to the J theta. Okay. This is the complex math bit, like I said, so for those of you who don't know what's going on, you can just kind of skip forward probably 5-7 minutes. Those of you that have an inkling as to what's going on, if you remember Euler's formula, e to the pi I is -1, or that's a result of Euler's formula. Euler's formula is, and I should have written this down, e to the ix, I believe, equals cosine x plus I sine x. It's a complex relationship between cosine and sine. This was used for a little background information. This is used to rationalize a polar coordinate system to a Cartesian coordinate system, and vice versa. So, the important bit to get out of this is probably this bit here. Specifically, well, yeah, it's this omega t plus phi. This is what describes the phase shift. This is what's going to, well, specifically this bit here, phi is used to denote phase shift. For those of you who stopped listening to when I said stop listening but are still listening, that's what this is. So if you do the complex math here with Ohm's law and using the proper impedance formula for the capacitor and the inductor, and you sum that all together, you can calculate the phase shift between the current and voltage in a system. So what you should see is, if I were to draw another, actually I can just scroll back up and use another graph. Depending on the impedance in the system, you will see something that looks like this. You'll see voltage and current being out of phase in some way. And again, the reactance in the system dictates how big a phase shift that is. So that is probably the most complicated thing when it comes to AC. It's the change from simple resistance to reactance and impedance and this complex system. You really don't have to know the complex system to be able to do things. A lot of stuff is already derived and put into much simpler terms, so it's much nicer. This theta is this theta here, for those of you wondering. It's the angle between impedance and ohms. So that was probably the most complex bit. This, if you've seen anything I did with the filter videos, this is where those formulas come from. This is the real magic behind how that works. That describes the phase shift and the attenuation of frequencies. So, ta-da! That's how that works. So yeah, that's probably the most complicated bit. So I guess what that just leaves is power. Now, the thing you have to remember about power is, again, if we're just going to talk about sine waves and cosine waves by extension, is that they are periodic. Meaning that you're going to have an area of positive power and you're going to have an area of negative power. And if you go on to a time of infinity, what that will eventually sum out to is zero power. But that's not really the case. There is still some power, power. Power is your light, a light bulb. Yeah, there we go. Not a fluorescent bulb. Going off script here. I'm trying to remember what the other kind of bulb is. Jesus. I cannot remember what the other kind of bulb is. The bulb with a filament. That lights up. That requires power. So there is still some power. And the key to finding the power is the same way to finding it through with DC. You have to find the current through the system, and you have to find the voltage through the system. And I think what power works out to is power, the apparent power it's called, is the square root of the real power squared plus the reactive power squared. So remember I said that in an ideal world, all that matters is the reactance. That's how that comes into play. The real power is... what's the real power? The real power has to do with... what does the real power have to do with? Real power has to do with the current in the system flowing through a resistive element, I believe. So that's how you calculate the apparent power. The apparent power, remember, is according to the periodicity of the wave, we shouldn't see any power, but yet there is apparently the apparent power, some power flowing through it. So that's how you calculate that. And again, you could derive energy from that being that over time. But yeah, that is it. I think I covered everything for alternating current. Hopefully I didn't scare too many of you off with some big math. It kind of had to be done because I'd get questions on it. But I guess that brings me to this point. If you do want me to go over some of the more complicated math, I will do it just for you guys. I kind of want to do it, but if you've managed to figure out what you need about alternating current from this, I guess you don't have to request it. But if you do want it, leave a comment saying, hey, we want this video. And I'll do it eventually. And I will be doing that video on inductors, so look out for that. But until then, I'm Human Hard Drive. Thanks for watching.